Today we'll be doing the first practice problem for homework number 5. So, to restate the problem, we'll do this with a picture. We have a steel ball, or lots of them, but we're only modeling one, being dropped into a vat of liquid. This steel ball has a diameter d of 0.01 meters, and it's made out of steel, which has a thermal conductivity of 40 watts per meter Kelvin and a density of 7,800 kilograms per meters cubed. Our thermal capacity is 600 watts per kilogram Kelvin. And finally this, again, we're cooling this ball off, so we need its initial temperature, which we know to be really hot, 1,150 Kelvin. Now when we drop it into this vat, it will be exposed to convection, where the temperature of our liquid is 325 Kelvin, and our convection coefficient is 25 watts per meter squared Kelvin. All right, so that's all of our information. Our next step, let's do an energy balance control volume. Okay, so we're just going to draw the ball again right here. I'm going to draw a control volume all the way around our sphere. Now by doing that, we're making an assumption that this entire ball is at a uniform temperature. Likewise, coming out of this ball, we have convection heat transfer, which means that that energy has to be coming from somewhere, so the temperature of our ball must be dropping as that heat leaves as convection. Okay, so we've done this energy balance. Now we're not going to write it out mathematically because, and this brings us to the approach portion, what we're going to do is we're going to see if lumped capacitance is valid. Lumped capacitance we derived using this, I believe, exact situation, a ball with Q convection coming out, decreasing in temperature. So if we can use the lumped capacitance approach, we can skip straight to a final equation. Okay, so let's begin first by doing what we should always do. Before you do anything with a transient problem, always check the BO number, which is H times the characteristic length divided by our thermal conductivity. Okay, now for a sphere, our characteristic length is going to be the radius divided by 3. So plugging in numbers, for H we have 25. For our radius, that would be half of our diameter, so 0.005 divided by 3. And we're going to divide that by the thermal conductivity, which is 40. When we do that calculation, we get a BO number of 0.001, which is really, really small. That's great because to use lumped capacitance, our BO number must be less than 0.1. So that means we can use lumped capacitance. So skipping straight to the final equation, we are looking for, I didn't even tell you what we're looking for. We're trying to find the time for the ball to cool to a temperature of 450 Kelvin. Okay, so we're looking for time as a function of temperature. We have that equation and it looks just like this. Density times volume times heat capacity divided by our convection heat transfer coefficient and multiplied by the surface area of our sphere. That whole thing is multiplied by the natural log of theta I over theta. And we'll remember that theta is just equal to a temperature minus T infinity. So theta in this case would be the temperature that we're trying to get to, 450 K. Theta I is our initial theta, so that would be the temperature we started at, 1150 minus T infinity. Okay, so we are looking for T, so we're going to solve for T. All we have to do is plug in our values. We have our density, 7,800. Our volume of a sphere, pi d cubed over 6. I had to Google that one, so don't feel bad if you don't remember that off the top of your head. Times 600, and that whole thing divided by h, which is 25. And that is multiplied by the surface area of a sphere, which is pi times d squared, 0.01 squared times pi. That times the natural log of theta I, or 1150 minus 325, divided by theta, or the temperature we're trying to get to, 450 minus 325. Okay, so we have this long expression. We know all the numbers. We just plug that in, and we get 589 seconds. Finally, some discussion, which I will just talk about. By doing the BO number and finding that it was less than 0.1, we then assumed that the temperature inside of our sphere was the same at any point. In other words, it was isothermal. In reality, there will be a small temperature difference between the center and the outside, but here we're saying it's negligible. And because our BO number is so small, our error is actually going to be very small as well. All right, that was our problem. Thanks for watching.